Welcome to week 1 of Our Energetic Earth. This is a MOOC that we're going to use to explore this amazing planet and some of its remarkable energy transformations and systems. And we welcome you. We're hoping that you're going to come along for the ride and explore these fascinating systems. In fact, I hope when you think back that you can think of some of the experiences that you've had with energetic systems. A time that you've gone out and you've perhaps enjoyed white water rapids on a river, or perhaps you've enjoyed the sound or the experience of waves at a beach, or perhaps you've been in a thunderstorm or even a more violent event. The Earth is full of the textures and the varieties of energy transformation systems, and that's what this course is all about. And what we're going to do in each week is we're going to start each week with a brief introductory overview that I'm going to give you of what we're going to be doing for the week. And then we're going to reflect at the end of each week on some of the significance and some of the observations. And that will be a kind of a pattern for us for the next few weeks. This first week, what we're going to think about is the biggest concepts that relate to energy for the planet as a whole. Those really big concepts are really remarkable. It's taken humans a great deal of time and effort to come to grips with these things, but they're very much worth the effort and worth the trouble. One of the first ideas that we have is that really fascinating concept of a budget. I don't know if you've ever planned a major event in your life, if you've planned a wedding or a major family event where you've wanted to do a bunch of special things, but you've realized that you couldn't spend as much money as you might want to. You've had to have a budget to make things work, a sort of a upper bound on the amount of money that you could spend. The Earth has a budget as well. The Earth has an upper bound on the amount of energy that it uses. And that upper bound is set primarily by the energy input that we get from the sun. And the first thing we're going to trace in the first week is what is that energy input and how it varies. One of the things that's fascinating is, much like money, energy on the Earth is not distributed particularly uniformly. Energy is in fact distributed quite non-uniformly, and we have areas of the Earth which are very rich in the amount of energy that they receive, and other areas of the Earth which are much poorer in the amount of energy that they get from the sun. It turns out that there's a fair bit of transfer that takes place between the energies that receive a lot and the energies or the parts of the Earth that receive less energy. And we want to look at those transformations and see how this energy conveyor works between different parts of the system. So we're going to look at that budget and look at it, the way it's allocated and distributed, and look at the way it relates to the Earth. And it turns out that one of the very fascinating and central ideas is a geometric argument. The Earth has a spherical shape, which means that there are certain parts of the Earth's surface which are oriented to be perpendicular to the sun, and certain parts of the Earth which are oriented that, in a sense, slant away or bend away from the direction the sun's rays. This, of course, gives us the idea of the polar regions and the equatorial regions. And those are marked by this decisive difference in their energy inputs and in the energy budgets that they have to live under. So we get that first idea of the geometric influence, and it turns out that that geometric influence is very strongly biased towards different times of the year. And that's because the Earth is oriented not perpendicular to the plane of its orbit around the sun, but in fact slanted away from that, which gives a very decided bias to either the northern hemisphere or the southern hemisphere. So one of the first things we learn is that there's single explanation really for why the Earth is colder when we move towards the poles, and why in fact we experience seasons. And the origin of both of those things arises from this concept of a budget and the concept of fixed input of energy perpendicular but then bending away for this geometric component. One of the background questions, which we're not going to answer right at the very beginning, but of course you should be thinking about, is what is energy anyway? What is this mysterious thing that we use to explain so many different processes and so many different variations? One of the key things you probably already know about energy is transformed in a simple device like a pendulum, which swings up and turns its motion into potential energy, and then swings down and turns it into kinetic energy. We have a conversion process of two different kinds of energy. If you watch a pendulum for some time, though, you'll see that it will gradually decay. It will no longer have a complete conversion of potential energy into energy of motion, but in fact it will gradually dissipate. And the bottom level of this energy transformation is thermal energy, and that turns out to be quite general. In fact, almost all forms of energy are interchangeable to a very large extent, except for thermal energy. It's the sort of the bottom foundation where you can get energy into thermal form, but it takes a lot more cleverness even to get any of it out. And it turns out there's very good arguments that we can't get all of it out. Some of it is irrecoverable in that form. And these ideas go together for one of our other key concepts that we're going to get right at the beginning of this course, which is the idea of energy cascade, of energy coming in at a top level in a fairly available form, and then through a sequence of transformations coming out at the bottom level, having experienced this process of decay. And in order to illustrate this, I thought I'd put on my screen behind me here a picture of a cascade of water. This is a waterfall where the water comes into the top level with maximum of potential energy, and it cascades through a sequence of steps, comes out at the bottom level with much the same basic properties that it had at the top, except it's lost that gravitational potential energy. And that's going to give us that secondary process, which is the idea that even within these transformations where energy is conserved, energy also decays.